Okay, so I told you now how we can select a slice in a certain object that we put in a large magnetic field, and by using a certain gradient that makes that the radio frequency pulse that we then would use afterwards to make a 90-degree pulse would selectively select only those protons that are feeling the exact right magnetic field as determined by the sum of the main magnetic field plus the gradient. Right? So that's how we do slice selection. Now, that means that we will still look at all the protons from a full slice. So now still, in order to make an image, we need to be able to look at the XY, say that this would be the XY plane that we select. Now we still need to be able to position the measurement in the XY plane because we need pixels at every position. So now we need to do a next trick in order to do that. And so we're going to do that again by using different magnetic fields. So if we look at 3 different protons at 3 different X positions, so we're now looking in the XY plane, so they're rotating in the XY plane after the 90-degree pulse. If I now would add a magnetic field gradient, so I would change now, while they're rotating, I would change the magnetic field in the direction of the X direction. What happens now is that, of course, since we know that the rotation speed at which they rotate, so their precession frequency is dependent on the local magnetic field. The higher the magnetic field, the higher or the faster they will go. So if I add a gradient in the X direction, what happens is that depending on the X direction, we will make them go faster or slower. And if we make them go faster or slower for a certain amount of time, so we switch on this gradient and then we switch off again, after we have switched it off, they start to rotate again with the same speed. But what we see is that they now change or they are rotating at a different phase. Because we changed, by speeding up some, we made them go before one, and by slowing some, we made them go a little bit behind. So the result is, if for a short period I have put this gradient, it means that I go from all going at the same frequency and at the same phase. Later on, after switching on and off this gradient, they go at the same frequency but at a different phase. So I have now phase encoded the position. So now, depending on the position of the proton in the X direction, I have changed its phase. And since with my coils I measure both the amplitude and the phase of the signal, I now can, depending on the phase that I measure, I now know in which X position we are. So now we have been able to, with first adding a Z gradient while doing the radio frequency pulse, we have selected a plane. And in that plane, if I now add a X gradient for a while, we can dephase depending on the X position. This is what we call phase encoding. So now we still have to find a way to encode, of course, the Y direction, because we need both. We need the tree, we need the plane, we need the X, and we need the Y to have a unique position of every point. And we do that now by adding another gradient. So what we do is first, in the XY plane, once they flipped, this is before the relaxation. Keep in mind, this is just before the relaxation. So what happens is they are going in the XY plane, all with the same phase and with the same frequency. I put on a gradient in the X direction, and now, for a short period, now I come in a situation where they all go with the same frequency, but with a different phase, and the phase will depend on the X position. If now I switch on a gradient in the Y direction, what will happen is that, of course, depending on the strength of the gradient, they will change their frequency. They will go faster or slower in the Y direction. And if I now measure while this gradient in the Y direction is on, what I see now is that every position in the plane is uniquely defined by a frequency and a phase. So we have used phase encoding in the x direction by switching on a gradient for a short time until they have dephased, switch it off, and then we have them phase encoded depending on the position in the x direction. Then we switch on a gradient in the y direction, which will change their frequency. And at that moment, while the gradient is on, we will see that we have a y position depending frequency. And if we now measure the frequency and the phase of each kind of proton, we will know exactly where it was. And if we then measure, of course, the amplitude at the same time, so based on the measurement of the amplitude, which tells you how large the vector is there, and then depending on its frequency and its phase, which tells me where the x and the y position is, we now have a unique measurement of a value for each different x and y position. Is that clear? So the way we do this is first we put the patient in the large magnetic field, all protons in the same direction. Then while we add a gradient in the z direction, we add radio frequency energy so that the protons in the plane determined by our z gradient are flipped by 90 degrees. Then we take off the radio frequency energy, we take off the z gradient. We then add a x gradient for a short period in order to dephase them based on their x position. And then we add a y gradient in order to change their frequency depending on the y position. And while this y gradient is on, we measure. So that's the whole principle, how we can do the measure.
Can you repeat this process, please?
Yeah. So we start with the starting situation where the body is in the big magnetic field. All protons are directed in this magnetic field, so in the direction of the tube. Now I change the magnetic field by at every position in the z direction by adding a z gradient. So I switch on the z gradient, which means that the magnetic field is slightly different in every z direction. And then I add the radio frequency energy in order to switch them, to flip them 90 degrees, but only the protons which are exactly in the right magnetic field for this radio frequency pulse that I'm using, they will flip. So I flip in one plane, in the z direction, I flip all the magnetic fields. So all these little magnets are now in the XY plane and they're turning around there. What I do now is in the X direction, while they're rotating, I switch on a gradient in the X direction. That means that now, depending on their position, and that's what you see, so this is after the flipping, in the XY plane, they are rotating at a certain frequency, determined by, at that moment, the local or the big magnetic field that they're in. So the magnetic field determines their speed. So here it's only the big magnetic field which is on. They rotate with the same frequency because they see the same magnetic field. And they rotate with the same phase because they were flipped together. This is immediately after flipping. So before the T2 relaxation, that is the next thing. So immediately after flipping, they rotate with the same frequency and they rotate with the same phase. Then I switch on an extra magnetic gradient in the X direction, so here the horizontal direction. And while this gradient is on, of course, where the local magnetic field is a little bit higher, they will speed. Where the local magnetic field is a little bit lower, they will slow down. And the result is then, after a while, they start to dephase, of course. Depending on the X position, they will dephase. And if I switch this X gradient on for a very limited period of time, and then I switch it off, what happens is that of course, they start to again rotate at the same speed, but they are put in a different phase, in a different direction, by switching on this X gradient for a little bit and then switching it off. So now I have changed the phase of the signal of so actually the direction of the vector, which is the phase. I changed it depending on the X direction. If now in this situation, I switch on a gradient now in the Y direction, what now happens is that I will speed up the ones which are in a higher gradient or in a higher magnetic field in the Y direction, and I will slow down the ones with the lower magnetic field in the Y direction. So that means that now, on top of the fact that in the X direction, I have changed their phase by switching on the X for a little bit and then switch it off, I now, while the Y is on, have changed their speed depending on the Y position. And now, every single pixel, so every point in space, now has a unique combination of a frequency and a phase. The frequency depends on the Y position, the phase depends on the X position. And the X phase I have changed by switching on an X gradient for a little bit, switch it off. And the Y frequency I have changed by switching on the Y gradient. So while the Y gradient is on, we see that we have a faster rotation where the magnetic field is slightly higher compared to where it's lower. And if I measure at this point, so after I first did a Z gradient plus RF pulse to flip, then an X gradient in order to dephase, and then a Y gradient, and while the Y gradient is on, I measure, every single point has a unique combination of a phase and a frequency that we have put on it and which is related to its position, and then a certain amplitude which will relate to whatever kind of relaxation has happened up to a certain point when we do the measurement. Is that more or less clear?
Yes.
One question.
Yes.
Why do not each pixel, as it is in a different phase, cancel out with the others, as it happens in the T2 model?
Well, because we don't dephase them so much, So, and the thing is, what you will see is, of course, you can only do a bulk measurement, and that's what we will see next. Is like what you need to do is what we actually do is we measure it by first dephasing a little bit, then dephasing a little bit more, then dephasing slightly bit more. So in that sense, you are right that what you measure is the sum of all this. So in the Y direction frequencies, we can measure all frequencies at the same time. But the phases we cannot measure on the same time. And there you're right. So what we actually do, and that is becomes in a minute, what we do is we actually do different lengths of an extra gradient so that every time we dephase a little bit more, and then we use all these different measurements that are taken at different dephasings, and then we can actually decode it later on and reconstruct.
Okay, thank you.
That's actually illustrated here partially. So this is actually how magnetic resonance sequences are being kind of plotted in some ways or being designed. So what I do, I switch on the slice selection, so the Z gradient. And while this is on, I put on the RF pulse, the 90-degree RF pulse. Once this is done, that means that we only have flipped the protons in a certain plane. Then I switch on a phase gradient and for a certain amount of time. And then I switch on a frequency gradient, and during this frequency gradient, I measure the signal. But what I do is I do actually the measurement at different, so this is an animation. So I do it at different strengths of this phase gradient. So in such a way that we can actually discriminate in different measurements the different phase components. So this is what a pulse sequence looks like. So this is what we do repeatedly. So that's what we do. And then we measure all these signals. And then we need, of course, to make an image out of this. And what you can already think is when we are talking about phases and frequencies, then you think immediately about Fourier transform. And so again, this is where the Fourier transform comes into magnetic resonance imaging. So what we measure is we measure a signal with different frequency encodings, so that contains different frequencies, and that is related to different phase encodings that contains different phases. So what I do is I can actually fill up a space with measurements that are taken at different, so I fill the matrix with measurements which are taken at different phases and different frequencies. And because I know that by design, I made these phases and frequencies correspond to a spatial location, what I do is if I do an inverse Fourier transform of this measurement, I will actually get my image. So what we do is with magnetic resonance imaging, we actually measure the Fourier space, which they call K space in here. And then doing a simple inverse Fourier transform, we actually get our images. So reconstruction by MRI is based on inverse Fourier transform, the simple type of reconstruction, where we use the simple phase and frequency encoding. So important, so to repeat again, keep in mind that the phase encoding gradient we do on before we measure and for a certain amount of time. And the frequency encoding gradient we put on during the measurement. As long as we measure, this has to be on, because that's the one that changes the frequency. And so here are some examples. So this is actually what we measure. And so this is the raw data that comes out of the MRI scanner with measuring different lines. So with every phase encoding gradient, we measure one line in the frequency space. And so we fill the frequency space during these different repetitions that we do. And once we have filled this, we do an inverse Fourier transform and we get the image that we want. Okay, now the thing is, how do we interpret it? So what now determines the amplitude of the signal that we measure? Because here what you see is the measurements are with our phase and frequency encoding. We know their position, but each pixel has a certain gray value. And then that corresponds then, of course, to different tissues in the measurement. So what now determines the amplitude here that we measure? Well, of course, it's the relaxation. So now, depending on when I measure, so the measurement itself has to be short so that during the measurement, there is no relaxation. But when we do the measurement, that, of course, will determine at which phase in the relaxation process we are. So the echo time is what we call the time when we measure. So it means like we start the sequence. So we start the sequence always with flipping, and then we measure after a certain amount of time, and that's what we call the echo time. And so depending on the echo time, where I measure, we will see that the T2 relaxation, because my measurement is happening in the XY plane. And keep also in mind, T2 relaxation is faster than T1 relaxation. So that means that if I measure after a certain amount of time, say now here, roughly say that I measure after, say, roughly 600 milliseconds, what happens is that the whole fat has already fully relaxed in T2, so has fully dephased. The signal is 0. So I measure nothing of the fat, even if I do space, so phase and frequency encoding, there is no signal anymore that I can measure, while there's still a lot of signal of water. And so by measuring here, I selectively measure water and I suppress fat. Fat becomes black, water becomes white. Now, the repetition time is when do I do my next flip for 90 degrees? And now, depending on when I flip, depending on how much it has already relaxed T1 in the direction of the field, that will now, of course, determine on what will be the amplitude when I flip next. So if I flip here, for example, so if I flip at the moment that the fat has become fully recovered, but the water is only partially recovered, if I now flip the vector, then my fat vector will be 100%, but my water vector will only be 50%. So if I then immediately after this second flipping now measure very, very fast, what I now do is now I measure the fat and I have less signal of water. And so by combining when do I measure and when do I flip again, I will actually be able to modulate the amplitude of the vector and have this amplitude correspond to a certain combination of T1 and T2. Keep in mind that they keep on happening together. So we have also a change because of them together. So because that's what you see. So if we look at the value of the amplitude, so there's an exponential decay with T1 and there's an exponential decay with T2, and it depends on when I measure and when I flip what in the end the value would be. And since they're all tissue dependent, we can actually kind of highlight specifically different types of tissue. So if I'm working with a very long echo time, so I measure very, very late, then I'm actually measuring predominantly the difference in the T2. If I measure with short repetition times, I'm actually more emphasizing the effect of the T1. Because if I wait very, very long before flipping again, then of course, all of them have recovered. If I have a very short repetition time, we don't see water anymore, but we will see fat. So this way, we can actually discriminate water-based tissues and fat-based tissues predominantly. That's what we look at. These are like the most extremes in some ways in our soft tissues. But keep in mind that the soft tissues, for example, gray matter and white matter also have a slightly different combination, and this will show a different amplitude. And here you see the effect of it. So what you see here is that if I do a T1 weighted image, what we will see is the water that would be in the ventricles. So in the middle of the brain, you have these holes that contain water, and also there's water surrounding the brain. So we see water is black because I'm emphasizing the T1 effect that suppresses the water. But the fat around the skin, we see quite well. If I'm now looking at long echo times, so this is at short repetition times, this is at long echo times, what I now do is now I emphasize water and I suppress much more the fat. So what you see now is that the water becomes bright. So we really look at water content, and what you see now is that the fat is being suppressed. When we do a combination, we can look, for example, at what's called a proton density, which just looks at how much signal do we have, how much protons are available there. And what you see here always is that look at the bone itself, there's almost no signal from bone, because it's only a little bit of fluid within the bone that you see, but the bone itself, the calcium of the bone, we don't see with magnetic resonance imaging, at least not with the normal proton magnetic resonance imaging that we are doing. And so this way we have the very typical views that are being taken, typical sequences that are normally being taken when we do this. Okay, so the thing is, this now relies on the fact that we are looking at, or we're trying to measure this relaxation phenomena, and we assume that the amplitude of the vector that we measure is related to this T1 and T2 relaxation. Now, the thing is, there are other things that would also change the amplitude. And one thing is that, of course, while we are measuring and we want to emphasize the T2, there is a T1 relaxation already going on, and that we don't see. Now, when we look at the dephasing in the XY plane, there is the T2 relaxation that's happening, and the T2 relaxation is because of inhomogeneities in the magnetic field because of surrounding different molecules. Because we have locally different molecular environment, we have a locally, because of each of these molecules is a little magnet, the total magnetic field there locally is different. Because of that, we get a different frequency, and then we get the dephasing, and that's the T2 effect. That's happening, we cannot do anything about it. But at the same time, what happens is that actually the magnetic field, our main magnetic field, is not perfect at all. It's not perfect because of the fact that the technology is never perfect, but it's also not perfect because there will be large changes in some tissues. For example, there might be some iron there available or things like that. So, and these things, which are magnetic field inhomogeneities, which are not because of the local molecular small differences, but because of the fact that we don't have an ideal magnetic field, that will of course induce also this dephasing, just exactly in the same way as T2, but we call this T2 star. So this is the non-intrinsic differences in the magnetic field, which is done by the external kind of circumstances, which is predominantly the machine, predominantly the inhomogeneities in the main magnetic field, but can also be because of some overall properties of the tissue that will make it slightly different magnetically. That's T2 star. Now, T2 star, so this kind of field inhomogeneities not related to the local molecular environment, these inhomogeneities are much, much larger than T2. So actually, the whole dephasing happens much faster than we would like because of the fact that the inhomogeneities are actually much more than what we actually would want to look at. Because we want to look at the T2 inhomogeneities, because that is the tissue that I want to look at. But our non-ideal scanner will actually make this worse. Now, fortunately, the T2 star inhomogeneities are related to fixed things, like, for example, a non-ideal field. And these are reversible. And actually, we have a trick to make them reversible. And the trick to make them reversible is actually that, so we first do a 90-degree pulse, we let them dephase, and at the moment that these are dephased, what we actually do is we suddenly change their direction by flipping them now 180 degrees. So we have first flipped them in the XY plane. They start to rotate in a certain direction, and they start to face in a certain direction. If I now flip them 180 degrees, what now happens is that they are still or back again in the XY plane, but they're now rotating in a different direction. We have changed the direction of rotation. And what now happens is, of course, now, because of this dephasing, the ones that were going faster first will now also go faster, but they now will rephase because they go in the different direction. And so if I now wait again exactly the same time, so we first flip, we let them dephase, then we totally flip them, so we invert them, and we let them now rephase for exactly the same amount of period as we first let them dephase. What we actually did is we have put them back together, but this is only the effect of the T2 star that we can compensate. We cannot compensate the T2 effect. And that's exactly what we want. So we want to compensate for non-ideal characteristics of our magnetic field. So this is the use of what we call a inversion pulse, or a 180-degree pulse, in order to compensate for the unwanted effect of T2 star of the inhomogeneities of the field. And so this is what some of these pulses would look like. So we first have a 90-degree pulse, and then the signal will go down very fastly because of this T2 star effect. Then we flip it, we let the signal go up again for exactly the same amount of time. And now the only thing that we measure is the slower T2 effect. So because these happen at the same time, the T2 star and the T2 happen at the same time. T2 star is much faster, but we can compensate the T2 star by flipping and letting it rephase. And so if I measure here now, what I do measure is I measure the true T2 effect. And then I'll wait for a certain repetition time, and I do exactly the same. So what we have added is a 180-degree pulse at half of our measurement time. And so this is like another pulse sequence that actually improves the image, because it partially, or it takes away many of the inhomogeneities that are not working well. Now, actually, the fact that we put on gradients, so what I told you before is putting on a gradient in order to do the X phase encoding, and then putting on a gradient to do the Y frequency encoding, that actually induces a dephasing also. So because of this, of course, we very deliberately would add a dephasing. But this is again a dephasing that we can compensate. So if I use a certain gradient and I do my measurement, what I can do is I can do actually the opposite gradient again in order to kind of cancel the effect of the first gradient. And so this way, we come to a much more complex way of doing it. So now what we do is we do slice selection. So 90-degree pulse while we have a Z gradient. Then we do a phase encoding and a frequency encoding gradient in order to do the measurement. Then I can potentially do a 180-degree, or I first do the encoding. Then I do the 180-degree pulse in order to compensate for the T2 star. And at the same time, I can use again a gradient to compensate for some of the gradients that we did before. And then you can do again a readout gradient in order to do this. And so this kind of idea of this whole combination of gradients and flippings and things like that, that's what we call a pulse sequence. This is an example of what they call the spin echo sequence, but it's not important. We're not going to go in detail. You don't need to know all these pulse sequences. If you're interested, you can obviously read that in the book. But the main thing that you have to keep in mind that we use a combination of flipping pulses, first flipping in order to get it in the XY plane where we're measuring, then gradients to either select planes or select positions, and then do encodings in order to make sure that we can measure and that we know where we are measuring, and then use potentially kind of total flip 180-degree pulses to compensate for non-wanted effects of non-ideal magnetic fields, potentially also using gradients to compensate for previous gradients with opposite gradients, and then in the end do the measurements. And the measurements are related to measuring in the Fourier domain. So I'm filling up with every measurement, I fill up one, or I do one measurement of one line actually in the Fourier domain. And if we then do inverse Fourier transform, then we have our image. Now here you see some examples of some problems of dephasing. So for example, if here you have like some iron particles, so in this case ferromagnetic particles, for example, in an E, you see that you get these artifacts. So these are really artifacts, and you can partially compensate some of these effects with some of these compensations. You will never get rid of it fully, but you can actually get less distortion in some ways in order to do some of these things. So now there's different ways to do these pulse sequences. As I said before, we're not going to go in detail. That's not too important. What is relatively important, of course, is, as I said before, what you can do is you can do this also in 3D. Yeah? So instead of doing a slice selection and from then on do the pulse sequence in order to measure one plane, what you can do is you can effectively indeed flip all of the protons in a whole volume and then use also Z gradients in order to do the readout. So to do a Z encoding by a Z gradient, so you do both a Z and kind of X encoding in this case, and then you do a readout in the frequency encoding. And you can change these, so you can intermittently change which is the phase encoding, which is the frequency encoding, which is the slice selection. You can do this in all directions. So that makes that you can use oblique planes, and you can do like the most kind of efficient way that you want to do certain sequences, depending on sometimes the resolution that you want in different directions. But keep in mind, it's always, you need a gradient to select the slice position. You need a gradient to change the phase to do phase encoding, and you need a gradient while measuring to change the frequency to do the frequency encoding. So that's the things that you need in order to do this. Now there's different ways to optimize this in some ways, because doing a full image like you see here, so where you measure the full Fourier space, you get a full resolution image. That takes, of course, a long time. And there's different ways that you can choose to optimize this. And some of the extremes to show you the effect, for example, is say that we want to do less measurements and we only measure in a smaller part of the Fourier space. What you see is that we only have the low frequencies then, and we get blurring, of course. When you get when you miss high frequencies in an image, you get blurring. Or you can only measure the high frequencies, and then it's the same as like measuring a gradient. So you are looking only at the very fast changes. So this way you can optimize depending on what type of image, what you want to emphasize in some ways. Okay, so here again an example of how these different things can look like. So if we look at proton density, for example, what you will see there is that we really can look at the water content. So the more water, so this is the unboiled egg, the higher the signal will be. The more cooked, the lower the signal will be. In these ones, the fat in the yellow of the egg, you don't see, that's suppressed. Well, when we do a T1 image, what you do see there is there predominantly you see the fat. You see the fat in the middle, and you don't see anymore so much the differences in the water content. So it's really important to know what type of sequence am I looking at in order to interpret it. So here's another example. So this is like a full 3D image. So these are the typical examples or the typical images that are being taken. So you take, for example, a full image of the brain that you have like in all three directions at a decent resolution. And you see, again, as compared to CT, you see much better contrast in the soft tissues. But keep in mind, as I told you before, the spatial resolution of MRI is less than CT. MRI roughly 1 millimeter, CT roughly 0.5 millimeter. So CT has better spatial resolution, but has much worse contrast for soft tissues. And so again, depending on what you want to look at, you will use different ways in order to do this. So here you see some other examples. So here is, for example, a pathological example where you see some cavities which are abnormal, and then you want to see, okay, is this kind of filled with fluid, or is this is this maybe a fatty infiltration, or is this a hard infiltration? Is this, for example, fibrous or whatever? So by using the different pulse sequences, we can try to discriminate the different type of tissue and then see what we are dealing with actually. Here's another example. So this is a fetus in the uterus. So you clearly nicely see the fetus. You see the brain of the fetus. You see the amniotic fluid, so the fluid within the uterus, and then you see the wall of the uterus, which is actually a muscle, and then you see tissue of the mother. So these are some kind of images that you can take, for example. You can actually go further. You can actually use this also for research. You can actually do continuous imaging over a longer period. And so here you see a nice example of really development, in this case of Echinopus. So that's like the early development of some type of frog, where you can really see how this is going on. This is, of course, done, because it's very small, in a very high field scanner. And this is, of course, done over a longer period of time. So this has, for research, you can dedicate the scanner and have it occupied for some time, which, of course, you cannot do in clinical practice. Because one of the things that also limits the use of MRI is that a person has to go into this tube. I'll show some images later on, for a certain time, and you cannot lie still for more than an hour, for example, during a scan. So that limits what you can do. But MRI is in principle relatively non-invasive, so that you can much easier do repetitive measurements as compared to, for example, a CT scanner. Here's another example of a research one where you have like a lot of mouse embryos, which you look at the same time, but you can nicely see the different organs in it. Okay, so the time, as we said before, to do the imaging. So the time depends also on how much time do we need in order to fill the full Fourier space. And what we need to do is, if we want to do this kind of consecutively, we have to wait a certain amount of time so that we have the full T1 and T2 relaxation. So we look at these kind of the repetition times and then the echo times. And the thing is that if you do it the regular way, to do perfect imaging in the traditional way, actually your imaging can take very, very long if you want to have a full 3D volume. So that means that actually the manufacturers have looked at different sequences that actually can speed up this process. But of course, it always goes at a disadvantage that we either lose some signal or that we have less resolution, so that we take less pixels. So all of these things are, again, optimizing in order to do this. But that means that there's like, when you go to a scanner, there can be like tens or hundreds of different pulse sequences, all with different properties. They either emphasize better T1, T2, they have a better kind of contrast, they might have a better spatial resolution. And as we will see further, you can actually even emphasize some other things that can be relevant for the imaging. So currently, there are more like low resolution, but very, very fast imaging sequences that are being used. But again, it doesn't matter. You don't need to know all these pulse sequences. You just need to know that there's different ways of doing it. And so that results in different ways of putting gradients and flip angles and things like that. And it can become quite complex at some point. So, but again, this is not that much of importance. Now, another thing which is important, as I told you before, when we started the classes, what we want to look at is we want to look at morphology. We want to look at the anatomy of the tissue, but we also want to look at some point potentially at function. We definitely also want to look at blood flow. And so what's happening now when we are doing images of, for example, vessels in which blood is flowing? Because that means that while we're doing the imaging, actually the tissue that is in the image, which is the blood, is actually changing, because blood moves out of the slice, for example, that we have selected, and new blood can move in. And actually we can use this, so this fact that blood is actually moving, and then it's each time that within the voxel that we're looking at, we have different blood coming in there, we can actually use that to specifically image the blood, to do angiography. And so that's the principle, is we select the slice, then we wait a certain period until the blood that was actually selected in the slice has moved out. And what we then can do is we can then, for example, invert the pulse. So we can revert this 90 degrees, which actually would now flip for 90 degrees this blood which is there. And this way, actually, we are measuring this. So the idea is that we do flipping pulses after a certain amount of time. So the idea is, first we flip in our plane. Now we wait until the blood has moved out. And what we now do is we flip back, or we flip now for 180 degrees, which means, or we flip 90 degrees. Now we flipped out again of the XY plane, but with this next second 90-degree pulse, if new blood came in that wasn't initially flipped for 90 degrees, now that blood will be flipped 90 degrees, and it's exactly this that we're looking at. So this way, by combining when we flip, when we reflip, or when we flip an additional 90 degrees, we can selectively encode or selectively flip pieces of tissue that we want to look at, in this case moving tissue, or in this case blood. And so this way we can actually selectively highlight blood, and that's what you see here. So for example, here in the heart, in the aorta, we will see that we now can highlight blood, and then we can also actually measure this. So we can measure blood flow as a function of time. So we can actually measure blood flow. It's very similar like Doppler. So we can measure blood velocities as a function of time, and then actually look at blood. Now we can also do this in a different way, is by using contrast agents. So just like we did with CT, where we use contrast agents that we bring into the bloodstream in order to highlight the blood, which in CT normally is not absorbing X-rays. What we can do is we can actually add contrast agents that change the magnetic properties, that predominantly change the relaxation properties of the blood, so that it actually can be highlighted in the images. And a very typical contrast agent that we use in magnetic resonance is gadolinium. Gadolinium is a metal, and because metal has different magnetic properties, actually by adding gadolinium locally, we very much change the magnetic field there locally. And we obviously change the properties of the tissue that we are measuring. Now, gadolinium is very toxic, so that's why we actually hide the gadolinium atom in a very, very large molecule, so that the whole becomes a contrast agent, which is safe. But that means that that is predominantly a bloodstream contrast agent that we use. So what is important is just remember that we need metals such as gadolinium as contrast agents there. And here is an example of a angiography. Well, there's actually two angiographies that are made with contrast agent. And then we can use image analysis, in this case, just maximum intensity projections to show this. But you see that you can actually get quite a nice resolution of these blood vessels. You really get a lot of details of blood vessels when we do this type of angiography. Here's an example of an aorta, and you see this actually is an aorta which is dilated. You see this bulb here at the aorta where it goes up. So that's a patient with a dilated aorta. Now we can also look at the dynamics of contrast, obviously. So because depending on when we inject the contrast, and when we do the measurement after injecting the contrast will be, of course, in different places in the body. So if we look at here the contrast, we see the contrast here, for example, in the aorta, and the contrast in a highly vascularized liver. But for example, we don't see contrast in these lesions in the liver. So that means that these are lesions, which is probably some kind of cancer, which is not very vascularized. And so here at another time point, we see that now the contrast is predominantly in the kidney. So that means that it's already starting to get washed out and is starting to be collected in the kidney. And so by looking with different sequences at different time points, we can actually see how contrast is being distributed. Also, when we look at the tumor, we see that at first there's no contrast in the tumor, but a bit later on there is. So that means that there is some perfusion, but it's slow perfusion compared to the perfusion of the liver, for example. Here's another, just an example of angiography. So where you really nicely see all the different components of the vessels of the brain, for example. Here you see a comparison. So this is actually an X-ray fluoroscopy that we said in the first class, where you do catheterization. So you bring a catheter to the origin of the artery, and then you inject iodine contrast. And this is an angiography made with an MRI. So where, of course, you don't need catheterization, okay? Because catheterization, especially of arteries, is very, very tricky. But you also see the difference now already. Yeah? While you see the large vessels with the MRI, you see it very well. The very small ones that you see with X-ray imaging, you cannot see because of the resolution. But this patient here, when you look at it, what you see here is you see this blob of contrast. This is actually an abnormality of the vessels. So this is like an abnormal growth of the vessels, but you can see that nicely in the MRI. So it might be that although the spatial resolution of the MRI is less than of the X-ray, it might be that you see enough. So it really depends on the application. Do we really need this high spatial resolution? Then we go to X-ray with the disadvantage that it's and a projection and that we need to catheterize. Or is the spatial resolution of roughly 1 millimeter enough? And then we can use, for example, an MRI, which is, of course, much, much less invasive. Right? Okay. I think that we can do another break. Let's do a break of a little bit more than 5 minutes. And then we continue with the last part of the class.